Alright, so we're here with chapter 5 from our book, and this is problem number 2. You can see I've already drawn a free body diagram for it. And the problem says the three ropes in figure P 5.2 are tied to a small, very light ring. Two of these ropes are anchored to the walls at right angles with the tension shown in the figure. What are the magnitude and direction of the tension T3 in the third rope? Alright, so I drew a free body diagram already of our system here. To solve this problem, though, we're going to need to have some components. So I'm going to draw the components in here for T3. So this would be T3 sub x, and this would be T3 sub y. Once I've got those now, I can pick a direction. I can pick the x direction, I can pick a y, and start with Newton's second law. I'm going to pick the x direction to start with just because that's what I like to do. We can see that it's not moving, so there's no acceleration. So we're in equilibrium, so the x component of the acceleration is equal to 0. Now if I just write what I have t3 sub x in the x direction, and I have t1 in the x direction, and that's equal to 0. Now because t1 is pointing to the left, I'm going to give that a minus sign. Now filling in for what I know and rewriting a couple things, I get that T3 sub x is equal to T3 cosine theta, and T1 is equal to 50. So at this point I'm kind of stuck because I have two unknowns. When I get stuck, I go to my other equation, which in this case is the y component of Newton's second law. And again, we're not moving, so the acceleration is going to be equal to 0. So now that we have the y component of the acceleration equal to 0, I'm going to do the same thing. I'm going to write t sub 2 minus t sub 3y is equal to 0. And again, I'm going to rewrite, fill in what I know. T sub 2 is equal to 80, and we get that t sub 3y can be rewritten as t sub 3 sine of theta. So now we've got two equations with the same two unknowns, and we need to find a way to solve them for what we'd like. So what I'm going to actually do is I'm going to go back to the x component of over here, and I'm going to say that t sub 3 is equal to 50 cosine over the cosine of theta. Then I'll take this information right here, I'm going to plug it in right up here. So I get 80 is equal to 50 over the cosine of theta divided by sine theta. And we should remember our trig identities that the sine over the cosine is equal to tangent. So when we do that, then we have the tangent of theta is going to be equal to 80 over 50. And if we take the inverse tangent of that, we find that theta is going to be equal to 60 degrees. Perfect. So now we have our angle. We can come back and we can plug it in over here. So we get T3 is equal to 50 over the cosine of 60, or T3 is going to be equal to 100 newtons, and I wrote 1,000. So let's just go back a little bit. Perfect. Now this 60 degrees that we're looking at, that is the angle that's right here. This is our theta. So to get the actual angle that we are looking for what the T3 is moving at, we want to actually get it from all the way around starting from 0. So in that case, it's going to be 360 minus 60, which is equal then to 300 degrees. If we had left it at 60 degrees, we would have gotten a positive y component, and clearly that can't happen in this situation. So to wrap it up, we get T3, the vector now, because we have a magnitude and a direction, is going to be equal to 100 newtons at 300 degrees.